Thank you for watching Part 4. In the previous part, I introduced installation of machine tools required for manufacturing and manufacturing of parts using machine tools. In installation of machine tools required for manufacturing, the necessary machine tools for producing special parts were installed. In manufacturing of parts using machine tools, the installed machine tools were used to produce custom parts. In Part 4, I will incorporate the custom parts I created in the Part 3 as designed in 3D CAD, complete the enclosure, and develop a program to operate the completed enclosure. First, I will introduce assembly of the enclosure. In the assembly of the enclosure, I will show the actual assembly process. First, I will assemble the bottom part of the frame structure. Next, I will add the rear side of the frame structure. I will add the lead screw and stepping motor on the lower side. After that, I will install the linear guide on the lower side. Then, I will connect the lead screw and linear guide using a plate. Furthermore, I will place the power supply circuit for the UV LED on top of the connection plate. Next, I will install the linear guide on the upper side. Next, add the upper lead screw and stepping motor. After that, I will install the upper optical sensor. Join the upper lead screw and linear guide with temporary parts for operation check. Connect the UV LED to the power supply circuit on the coupling plate and also add a fan for cooling. Attach the cover to the UV LED and fix the UV LED to the coupling plate. Continuously, I will separately assemble the upper frame structure. First, I will start by building up the frame structure. Next, I will assemble the main board to be attached to the upper frame structure. The main board is created by soldering electronic components onto the board. When soldering, the key is to hold near the tip of the soldering iron to ensure accurate aiming. In this way, the main board is completed. The completed main board will be attached to the right side of the upper frame structure. Furthermore, I will attach the operation LCD to the front. The operation LCD will be connected to a specified connector on the main board. The upper frame structure that has been constructed in this way will be connected to the lower frame structure. The base part is also assembled separately and connected so that the frame structure is placed on this base. Next, I will attach the transparent LCD to the UV LED cover. Furthermore, I will install the main power supply on the left side of the frame structure. Then I will replace the temporary parts for operation confirmation on the upper side with the finished linear bar. By replacing the linear bar with the finished one, the platform can now be installed. Next, I will attach the aluminum top plate to the top of the frame structure. In this state, dust might settle on the transmissive LCD, so I will attach an acrylic panel for protection. In this way, the protective acrylic panel is attached, safeguarding the transmissive LCD. Next, I will attach the side panel to the side of the frame structure. The side panel can be attached to the frame structure by aligning it with the protrusions designed for fitting. After attaching all the side panels to the frame structure, it looks as follows. Next, I will add parts to the top panel to allow the resin tank to be installed. After installing the resin tank in platform, it appears as shown above. Finally, I will attach the UV top cover to block external UV light. And last, the hardware of the 3D printer is complete. Let's remove the protective film from the side panels and UV top cover to see the appearance of the completed product. The actual finished product has almost the same appearance as the enclosure design on the computer, because it was assembled according to the 3D CAD design. Compared to the previous creation, the Windows 10 equipped electronic dictionary, I believe the quality is overwhelmingly higher this time. However, I cannot rejoice just yet. This is because software has not yet been developed for this 3D printer. In other words, it cannot even be started at this time. Therefore, in the next section, I will introduce the software development process. In software development, I will create two main types of software. The first is the firmware to be installed in the 3D printer itself. The second is the dedicated software to send 3D printing data from a Windows machine. First, I will introduce the development of the firmware for the main unit. Since the processes executed by the firmware are diverse, it is unrealistic to create the entire firmware all at once. Trying to create the entire firmware at once is like expressing all the operations of the firmware in a single sentence. The above sentence is an attempt to explain the operation of the firmware in one sentence, though. Naturally, it is disorganized and the relationship between each element is difficult to understand, making it meaningless. Such complex tasks can be solved by breaking them down into smaller tasks. Based on this idea, when I break down the firmware, I find that it is a collection of control processes for electronic components. Consequently, it is then obvious that the firmware can be completed by coding each control separately and combining them at the end. Introducing the implementation methods for all the controls would not fit into the video, so this time I will focus on the control of the operation LCD. Ultimately, LCD control is synonymous with being able to freely change the color of any pixel in any position. This is because any image is a collection of pixels. Therefore, any image can be displayed by rewriting each pixel in sequence. In conclusion, in extreme terms, LCD control can be achieved simply by being able to change the color of a specific pixel within the LCD. In fact, Render Tool, a self-made library that rewrites the LCD display content based on this design concept, defines a set pixel function that allows the user to change the color of pixels at any position. Other functions include the draw image function for drawing images and various shape drawing functions. However, consistently, all these drawing functions perform drawing by using the set pixel function. For example, the draw fill box function, which is used to draw filled rectangle, enumerates the coordinates of the pixels to be rewritten and passes those coordinates to the set pixel function, thereby rewriting the LCD screen. With this design, I believe the code has become both less prone to bugs and highly versatile. Additionally, basic components of the user interface, such as buttons, icons, and progress bars, can be easily utilized alongside screen transitions and UI animations through the library UI Render, which I developed. By combining UI Render with Render Tool, the foundation for creating the user interface is complete. However, to create the user interface, it is necessary not only to have the foundation, but also to design what is built on this foundation, namely, a good UI that delivers a great user experience. Here, I will introduce the points I focused on to create a good UI along with the actual UI design. What I prioritized the most was ensuring that desired features can be accessed intuitively with a minimal number of operations. Taking the main menu, the first screen displayed upon startup, as an example, it can be seen that frequently used functions like print and settings are placed in easily selectable positions. Additionally, by classifying features hierarchical, even less frequently used functions are made easy to access. Furthermore, efforts have been made to ensure intuitive operation by maintaining consistent button placement. The next point I've devised is making the connection between screens clear. Specifically, the device is designed to insert animation when the screen switches. Without animations, screens would transition abruptly, creating an unnatural impression. While there are other efforts, the overall UI design has been structured based on these principles. Through these efforts, I have achieved a user-friendly and cohesive UI design. In this way, the firmware has been completed. Next, I will introduce the creation of dedicated software for transmitting 3D data from a Windows machine to the 3D printer. The dedicated software I created incorporates the above-mentioned features. The 3D model loading feature allows STL format 3D data to be loaded. Since STL format is widely used, implementing this loading feature allows the use of a vast range of 3D data. Let me demonstrate how it works. 3D data can be loaded by dragging and dropping STL files. The viewpoint can also be switched using mouse operations. The loaded 3D data can be edited by clicking the displayed object to select it. Basic processes such as rotation, scaling, and translation can be applied to selected 3D data. Scaling can be set to a different magnification factor for each axis. In rotation, different rotation angles can be specified for each axis. Next, let me introduce the support material generation feature. Support material refers to pillar-like structures that stabilize objects during printing. To ensure successful printing, it is necessary to add support materials at optimal positions on the printed object. Therefore, the software I developed implements two methods for adding support materials. One is the manual addition of support materials, and the other is the automatic generation of support materials. Let me demonstrate how it works in practice. Manual addition of support materials can be accessed through the Support Material Addition feature. Support materials can be added by specifying the contact point with the printed object and the landing point of the support material. The positions of the contact point with the printed object and the landing point of the support material can be specified by clicking on the screen. Additionally, fine adjustments can be made, such as the length of the tip, thickness of the pillar, and contact radius with the printed object. Next, let me introduce the support material automatic generation feature. Automatic addition of support materials can be executed with a single click. The self-made automatic generation algorithm detects the positions where support materials are needed based on the shape of the 3D model and adds them at optimal locations. Furthermore, by changing the settings, support materials of specified shapes can also be automatically generated. The automatically generated support materials can be individually edited, allowing detailed adjustments. Continuing on, let me introduce the slice data generation feature. 3D printers print by repeatedly stacking cross-sections. Therefore, it is always necessary to calculate a cross-section of the printed material before printing. This feature, which calculates the cross-section, is the slice data generation feature. Let me demonstrate how it works in practice. The slice data generation feature can be accessed from the tab in the upper left corner. The name of the slice data can be specified through the text box. Clicking the Execute Slice button initiates the slice data generation process. The self-made algorithm for calculating slice data has been optimized in parallel styles for increased speed. As a result, the slicing process can be executed at a speed equal to or greater than that of other general-purpose software. The generated slice data can be viewed from the software for cross-sections of each layer. Finally, let me introduce the communication feature with a 3D printer. The dedicated software is equipped with features for transmitting slice data to the 3D printer via wireless communication and for remote operation. The setup for wireless connectivity can also be automatically performed by connecting the 3D printer to the computer via USB. Let me demonstrate how it works in practice. The initial wireless communication setup can be completed automatically through USB connection. After establishing the USB connection, simply clicking the Next button completes the wireless setup. The setup progress can also be monitored from the 3D printer's operation screen. Finally, setting a name for the 3D printer completes the setup process. After setup, wireless connectivity enables remote operation and slice data transmission. Through remote operation, the 3D printer's operation screen can be operated from the PC software. The self-made display rendering system achieves relatively low latency remote operation. Slice data can be transmitted wirelessly. With this, both the printer firmware and PC software are complete, making it possible to fabricate objects with the self-made 3D printer. To verify the printing accuracy, I actually printed an object like the one described above. This object measures 40 mm in width and length, and 10.6 mm in thickness. Let me show you how it looks during the actual printing scene. The printed object is fabricated in a way that adheres to the platform. After removing the object from the platform and cleaning it with IPA, it appears as follows. Since I used transparent UV resin for printing, the result is a transparent finish. Now I will measure the width, length, and thickness of the printed object. Although this is a simple measurement, it recorded a very high accuracy, with an error of 0.01 millimeters. The most distinctive feature of the 3D printer I developed is its ability to expand the fabrication area by moving the transparent LCD. Therefore, as shown in the video, I tried printing an object larger than the size of the transparent LCD. As you can see, the printing was completed successfully, even with the expanded printing area. Verify the printing accuracy in the same manner. By calculating the difference between the target values and measured values, it was determined that the maximum error is within 0.02 millimeters. I think this dimensional accuracy is excellent as a stereoorthogonally 3D printer. This precision is automatically achieved through the dimensional correction algorithm implemented in the software I developed. Seams are present in the printed objects because the 3D printer I created fabricates them by moving the transparent LCD. However, as you can see, the seams are barely noticeable due to the high positioning accuracy of the transparent LCD. Although it is hard to detect, there is actually a seam at this position. The cost of the 3D printer, calculated based solely on the component expenses, was approximately $460. Considering both the fact that it was built by a university student with no prior experience and the low cost, I think the completion level is acceptable. In the next chapter, I will undertake the final mission, making a friend. As you know, making a friend begins with deciding on the design. Since I am not an expert in making friends, I will design friends with the help of AI. During my journey to find a friend I liked, I encountered the following companion. He is modeled after a pound-sized wolf cub. And upon closer inspection, it has 7 fingers. Using this design image as a reference, I created a 3D model in Blender. Since it was my first attempt at character modeling, there were many shortcomings, but I managed to shape it somehow. Next, support material is added to the 3D model, and then printed. After removing the printed object from 3D printer and cleaning it with IPA, it appeared as follows. Upon magnifying the surface, I confirmed that even the detailed fur patterns were successfully represented. After processing with airbrush painting and other techniques, it ultimately achieved the following appearance. The iris pattern was printed onto sticker paper and applied to the model. Additionally, the iris was coated with UV resin in a spherical shape to represent the cornea. Thus, having made friends, the true goal, ramen with friends, is put into action. Thank you to Chukaidama for their cooperation in recording this video. I sincerely appreciate their support.
Matsudo-san.
It was a wonderful meal. Thank you.
He built his own 3D printer and made it realize that he could make friends. However, for some reason he did not feel refreshed on the way home from the ramen shop. Clever? He searched online and tried to find out why. Then, he stumbled upon the proverb, "Food tastes better when eaten with a large group of people." The conclusion he reached was,
I see. I didn't have enough friends.
that was it. He interprets the meaning literally and comes up with the idea of printing more friends. Yes, he will complicate things. It seems he will need a bit more time to find happiness.